Hello, everyone. I'm Phil. And today I'll be talking about RL under latent dynamics towards statistical and algorithmic modularity. And this is joint work with Dylan, Nan, Akshay, and Zach. And as the title suggests, I'm going to be thinking about reinforcement learning in big spaces where the dynamics are dictated by a simpler latent process that is unobserved. And I'm going to ask that this problem, I'm going to ask when is this problem as easy as the latent problem? So if the latent problem has some complexity, can you solve the full version of this problem with the same complexity? So a lot of environments can be summarized by simpler MDPs if only you had some magical representation. So if you think of a rover exploring around, what it actually observes is like high resolution images from a camera. But what it actually needs to know is just its location on the map. So it's mapping down to a much smaller space. And if you had that representation, you could make plans and explore much easier than you would if you were working just on the high resolution image. So one would hope that when you have this kind of structure between observation and latent space, RL for these settings should just be as easy as some representation learning and then some latent RL on top of that representation. So in some sense, this whole work is just trying to ask this question and formalize it and check if this is actually possible or not. I'm just going to try to convince you most of all that this is a very beautiful problem to work on. The definition of a good representation for RL is very unclear. What is a good representation for RL? Finding a good representation needs a good data set, but collecting a good data set without a representation is itself very hard. So they're kind of intertwined in a very beautiful way. So in fact, empirical works already do representation learning. There's like this zoo of representation learning procedures that they propose. And if you do use them, it works much better than when you don't use them. So empirically, it definitely helps to scale. In theory land, we're a lot more behind. So all of the positive results that we have for RL under latent dynamics need restricted dynamics models. So we need to assume that the latent space is tabular or is an LQR or something like that. And furthermore, the algorithms that you get are very intricate and complicated and hard to analyze. And they're not particularly modular in the sense that there's a representation learning scheme that is proposed to use in conjunction with a very specific algorithm. And if you disentangle them, neither might be useful on their own. So the goal is to just get simpler and more general RL under latent dynamics. So basically, what are the fundamental principles, both statistically and algorithmically, for RL under just general latent dynamics? We're going to study this in two different ways. The first one is what we call statistical modularity. So if a certain model class is tractable when you observe it directly, but then you make it latent and you observe emissions from it, defined shortly, is the corresponding latent dynamic setting tractable? So does statistical tractability of a latent problem extend to the rich observation version of it? And then you can push this a bit further, and you can ask that, in fact, you can solve the latent dynamic setting by just reducing to your favorite latent algorithm and only knowing that it's low risk for the corresponding latent problem. So can you just feed it a representation and get it going? Okay, so just to define a little bit what this RL under latent dynamics thing is, a latent dynamics MDP has two ingredients. The first is a latent MDP, MLAT, which is just operating on some latent state S. The second one is an emission process from the latent states to the observation space. And we assume that it's decodable in the following way. Basically, if there's two distinct latent states, they map to two distinct distributions of observations. So this makes everything Markovian. There's no partial observability. It just makes it makes life easy, but what you want to do is you want to avoid paying for the complexity of the observation space. And the dynamics evolve in the following way. So you get an observation X, you make an action based on that. The reward comes from the latent reward function, S. The next state comes from the latent transition distribution, again from S. And then you get a new emission from the emission for the state. So you only observe the X's, the observations, but the dynamics are completely determined by the latent states. And because of the decodability assumption, there exists a perfect decoder that maps every observation to a latent state. And we assume that you have a realizable class for these guys. And then the goal, informally, is you just want to pay whatever the latent complexity is plus log phi. And this log phi is just encoding that you can do supervised learning over the decoders. Okay. Any questions about this setting? Cool. So this goal that I stated was a bit informal. Let's try to formalize it a little bit. What are the MDPs that you're actually playing against? What is the class of MDPs that you're encountering in this latent dynamics problem? So there's a fixed set of features phi and a fixed set of latent MDPs, and you're playing against all possible latent dynamics MDPs where the MDP is from the latent model class and the emissions are decodable by some feature in your feature class. Right? Yes? Great question. What I want is what I call statistical modularity. So let's just let comp be the statistical complexity of a model class. What I want is that the complexity of the big class is a polynomial function of the complexity of the small class times with some extra log of phi factors. So for example, if you knew a lot about the latent process, but the observable process is out of your purview, can you actually just get a statistical rate that reflects your knowledge about the latent process? So as if you assume the latent space is tabular, it implicitly means you're happy paying S factors, but not X factors. And then we know that this is possible if the latent space is tabular, but it might not be possible otherwise. Exactly, yes. So yeah, this is encoding your function approximation conditions, like your biases about the latent space, just in a very abstract way. Right, so there's, just to reemphasize, there's some latent model class that you can solve with some complexity. Can you solve the latent dynamics version of this, which is all MDPs, where this MDP, where the latent process comes from the model class that you know. Cool. Unfortunately, you can't get this in general. So unfortunately, for model classes beyond tabular, you might not be able to get this, as illustrated by this lower bound, which is a bit depressing. But what it says is there exists a decoder class of size n and a family of MDPs of size 1, where the complexity of the latent class is just 0, but solving the latent dynamics version of it up to a constant scales with at least n. So in some sense, you have to just try all the possible decoders to find an optimal policy, even if you knew what the optimal policy would be in the latent space. So the latent MDP is fully known to you, but the complexity for solving the observation space problem is like at least the latent size, or 2 to the h, or number of decoders. Right. The intuition for the construction, somewhat quickly, is just that there's n different binary trees. You just start in one of them uniformly at random. In each tree, you want to go to the corresponding leaf. So if you're in tree 1, you want to go to leaf number 1. If you're in tree 2, you want to go to leaf number 2, and so on. This is all in the latent space, but the emission process, we can define it to just permute the indices around. So now, when you're facing the observations, you don't know which index to go to. You're in tree number 2 for you, but you now have to go to leaf number 1, but you don't know the amount that things are shifted by. And basically, we're just showing that you have to do exhaustive search to figure this out. There's no way to just do some supervised learning of a representation because of the specifics of the RL problem, where you need sort of like a globally accurate decoder. Even more depressing is that as a corollary, a lot of function approximation settings are found to not be statistically modular just because you can embed all of those assumptions into that one MDP that we have. So here's a big table. On the left is just a setting of different function approximation assumptions, like linear mixture, Bellman rank, coverability, linear MDPs, etc. On the right is just whether or not they are modular or not, in the sense of the definition that I gave. So I'm not going to go over all of these. It's not that important. Some of these upper bounds are also new, but I don't have time to talk about that. All of these negative results can be embedded into the construction that I showed earlier, which directly implies that you can't get tractable sample complexity for all of these problems. So some latent assumptions are useful for solving the latent dynamics problem, and some are not. And unfortunately, we don't have a unifying understanding of what makes a latent setting useful or not for solving the latent dynamics problem. Okay. Any questions? Cool. So now I'm going to talk about algorithmic modularity. Oops, too fast. So the question here is, if you had your favorite low-risk latent algorithm, can you interleave it with a representation learning procedure to get low risk for the latent dynamics problem? So the way that this works is that the representation learning oracle feeds you a feature. The latent algorithm plays using that feature, gives you some data, and then you update the representation learning, and then you just go back and forth until you can hopefully get a low-risk policy. We have to be a bit, we have to clarify how all these things are working. So the way that it works is that the representation learner is going to choose a representation based on all the data so far. You're going to play for capital K rounds your latent algorithm. It chooses a latent policy. You can't actually deploy that because you don't see the latent space. So you just deploy this policy instead. The policy composed with the feature that you found. You collect a trajectory. you can't feed that trajectory to the latent algorithm, so then you just give it the compressed trajectory. So all of the observations get mapped through the representation, and then this is the data that the latent algorithm observes. And then you just go back and forth. Okay, so to avoid all the negative results and the positive results from before, we're just going to make some additional assumptions. The additional assumptions are going to give us very strong results. In particular, we're going to get results that give universal reductions, like regardless of the latent algorithm, you can do this procedure. The two different settings are, the first one's called hindsight observability. So what you do is you get to observe the true latent states at the end of each trajectory. You cannot use them for deployment time, but you can just get them for training. And the other setting is that you can do representation learning not just with a set of features, but with a set of latent models. So you can model the latent dynamics directly. In this second mode, you have stronger function approximation, but you don't need additional data. Namely, yes, what's up? It's going to be clarified a bit later, but basically the representation learning is going to fit a feature and a latent model together. It's going to create some representation learning loss that is trying to fit the latent models. But you need to assume that the representation learning can do that. Yeah. So the two different representation learning oracles that we propose, in the hindsight setting, you can do sort of online classification with the 0-1 loss. So you want to find a feature that has low just classification error, which is possible because you observe phi star as a data set. You can do this by just de-randomizing an exponential weights mechanism. And the assumptions are just feature realizability and the hindsight data. In the online setting, what we do is we do quote-unquote self-prediction or by simulation losses. So what you're doing is you're fitting a latent model and a feature that minimizes this kind of loss informally. I can't write the whole thing here. But you're trying to model, you're finding a feature such that if you go through the feature and do the latent model, it's the same as going one step in the observation space and then compressing that one. This loss has many different solutions beyond just the true decoder. You can have zero loss by just compressing everything together. And to avoid this kind of degeneracy, we tie break by picking the optimistic latent model among all of these. And we show how to estimate this thing. It's some de-biased version of maximum likelihood with a latent optimistic bonus. And the assumptions here are that you need a true feature, the true model, something called latent model completeness, which just asks that this target on the right-hand side can actually be expressed as a latent model. It might not be a priori. And then we need coverability as well. And then the results, informally, are that in both cases, if you have these respective assumptions, using either oracle for an arbitrary latent algorithm, the risk that you get from the reduction is more or less just the risk of the latent algorithm on the model class plus the regret of the representation learning. So this holds for any latent algorithm. So it's what we call a universal reduction. And if the latent algorithm has low risk and the representation learner has low regret, this whole thing is sublinear. Cool. Yeah, so I guess I'll pause for questions. Any questions? Mm-hmm. Sure. Mm-hmm. Sorry, I didn't catch the question. Mm-hmm. I don't know. I haven't looked at how these things scale with misspecification. I know that there is a paper studying the LQR in this latent dynamics setting, and they do have a negative result for misspecified features. I don't remember off the top of my head how it scales, but people have looked at this. Yeah. Decoded, well, yes, they do. But then the lower bound is used to justify it. So just a quick summary. Excuse me. Okay, just a quick summary. In the statistical part, we defined sort of what it would mean. Sorry. We defined what it would mean for oh, God. Yeah. Let's try again. Okay. So we gave a definition of what we think it should mean for RL under general latent dynamics to be statistically tractable. We saw like some positive and negative results, mostly negative, that this is not possible. And it would be very nice to get a unified understanding of which assumptions are useful and which are not. In the algorithmic part, there was this like observable to latent reduction. We gave representation learning oracles under 2 different settings and showed that you can get universal reductions. Here there's lots of open questions. So like, are there side information assumptions that are weaker than hindsight that still let you do sort of like simple RL with latent dynamics? In the online setting without that kind of data, how do you get an efficient representation learning procedure that is useful? So in particular, can we remove the latent optimism that we used for the self-prediction loss or the by-simulation loss? And yes, that's it. Thank you. What's up? Well, the root of the hardness, okay, I've thought about this a lot. I don't have a good answer. The root of the hardness is that even if you know the latent like data about pi star, like q star, anything you want that's related to star is not useful. So like linear q star doesn't work. Even just like, for example, if you make like Bellman rank only refers to value functions with respect to the optimal Bellman operator. But things get jumbled around, so that Bellman operator is not useful. Yeah, the low state action occupancy only refers to optimal policies, is not useful. If you instead make it for all policies, it might be useful. This is actually open, we don't know this one. Things that tend to make dynamics assumptions instead of value function assumptions are useful, especially if it holds for all policies. So this like low state occupancy one If it holds for all policies, you're good. If it holds for optimal policies only, you can't do it. It just means all the occupancies can be written linearly for some unknown feature map. Then you can run this like bilin UCB because it has bilinear rank. The thing that unifies all the green checks, incidentally, is coverability for all policies. But we were not able to give a positive result for that. So that's a really interesting open question. Yes. What result do you want exactly? Sure. Oh, I see. It's a bit hard if you don't have the like decodability structure. If it's an arbitrary POM DP, like well, statistically it's already solved, isn't it? Or you want it by reduction? Let's see. I don't know. That's a good question, though. Yeah. I'm not sure.